We now know, or at least should know, the ways in which we take derivatives. For all these different kinds of functions, let's put these derivatives to use. We had applications that were particular, our growth models, but let's talk more generally. Most of the time, the applications of derivatives change by situation, but almost all of them seem to have something in common. Because we saw how universally applicable derivatives were, we can use them in so many different places, they show up all the damn time. Extreme values. What's my fastest reaction rate? If I add a catalyst, what does that do to that chemical reaction? If I have a product I'm selling, where am I going to make the most money? Where am I going to pay the most taxes? What production level, what situation arises, I look for the highest or lowest. I want to minimize my costs. I want to look at the extremes of a function. If I have a value in the domain of my function, x equals c, the y value f of c is the absolute maximum value of f on the domain D if it's the largest y value that comes out. If such a number exists, we say that the function has a maximum at x equals c, and the value is f of c. I can change one word here. If I change maximum to minimum, the only thing that changes is the direction of this inequality. So in general, I can look at a function. Ideally, graphically, I can identify these points very easily. Here are two graphs, page 276 of the textbook. In this top picture, I hope it is clear, we have a maximum value of 5 at x equals 3. We have a minimum value of 2 at x equals 6. In the lower picture, I have an absolute minimum value, whatever this y value is, f of a. I have an absolute maximum value. It's whatever this y value is, f of d. But they've labeled some other points in here. I've got b and c and e floating around in this picture. What's going on there? What's going on at b? Well, that's not the overall highest point. But if I were to restrict my field of vision and only look at x's close to b, isn't that the highest spot? Not overall, but in some little neighborhood? Same thing with c. If I restrict my field of vision to just looking around c, that's the lowest point in that little neighborhood. Same thing with E. By changing my viewing rectangle, for lack of a better term, I can look locally for an extreme. And that's what we're going to call these local or relative extremes. This third figure, I have exactly that sort of picture. We've identified the little section of x's that we're looking at with those vertical blue stripes. So I can change this definition just a little bit. a local or relative maximum at x equals c means that I have the highest value in some interval I containing c. Usually, we insist that that interval not have c at one of its edges. Again, same claim, change one word, change the direction of the inequality. Now, an absolute maximum will also be a relative maximum. An absolute minimum will also be a relative minimum, but I don't have to look at the whole function, I just have to look in some little bitty area. Questions so far? My terminology here. What's the graph of my function f of x equals x squared look like?
Parabola.
Give me a little more of a description. Yes, it's a parabola.
Parabola that opens upward because it's positive.
Opens upward. And that means that the point 0, 0, the vertex of this parabola, is the lowest point, and that means we have an absolute minimum. But Leo, as you said, this parabola opens up. It keeps going up, right?
Yes.
No matter how far I go to the left or the right, I keep going up. We have no absolute maximum. So, using the terminology I used earlier, this has a minimum value of 0 at x equals 0. This again is the graph of a parabola. Quadratic function gives me a parabola. Because the leading coefficient is positive, this parabola opens upward. So once again, I know, before I've done any work, that this function has an absolute minimum. Now for the $64,000 question. What is that minimum value? Where does it occur? Fortunately for us, this is a method we learned in algebra class. The name of the point where this minimum occurs. The what of my parabola? vertex. Way back when we did conic sections in trig class, when we did completing the square in algebra, we learned the coordinate formulas for that vertex. If I remember correctly, the vertex, we called them H and K. We had a horizontal shift and a vertical shift. We wrote it as a completed square, and there was a formula that allowed me to find H. Anybody remember that formula? Here's a hint. It's living in the quadratic formula. It's hiding in the quadratic formula. Hey, wait a minute. The quadratic formula, negative b plus or minus big ugly square root over 2a. Just throw out the square root. There's my formula. Oh, so I can take these numbers. A is 1, B is 8, C is 13, and I can plug those in here. So there is where my minimum occurs. My minimum occurs when x is equal to negative 4. That does not tell me what the minimum value is. Get that, I need the corresponding y value. So I need to get, oh, wait a minute, I didn't use f, I used g. G of negative 4. So I plug in negative 4 to the equation I've got up there. Negative 4 quantity squared plus 8 times negative 4 plus 13. 16 minus 32 plus 13 is negative 3. So the vertex for this particular parabola is at negative 4, negative 3. My minimum value is negative 3. It occurs at x equals negative 4. I can check, because I have this amazing piece of technology in front of me that allows me to graph parabolas and other things. So I can graph my g of x here. X squared plus 8x plus 13. And I see exactly as we predicted. When I put in negative 4, my y value is negative 3, and I am at the vertex of that parabola. I could also do the completing the square process, which would give me the h and k in the square complete form. Now, I'm really happy about this, but it relies on a bunch of algebra tricks. That's not helpful. Questions? So what happens when I make my equation more complicated? At this point, I don't know very much about cubic equations. I have to dig all the way back to chapter 2 of the algebra book and ask myself, what do I know about anything that looks like a cubic equation? Well, I could graph this right on my calculator. I could see what's going on. But let me make some more general observations. In a cubic equation, I have end behavior. I know what happens as we go off to the left and off to the right. Like in a parabola, I knew both ends went up. In a cubic equation, that power is odd. which means one end goes up and one end goes down. The number in front of that highest power tells me about the right end. Since it's positive, the right end is going up, which means that the left end is going down. So this graph looks like this. It might wiggle in the middle a bunch, but it looks like this, which means what happens as x goes to positive infinity? It keeps going up. Do we have a maximum? No absolute maximum. We're going off to infinity. What happens as we go to the left? Which means there's no minimum. Any sort of extreme behavior we have for this function must be local. Simply by looking at what I know algebraically. There are no absolute extremes. So let's take a look at the sketch. Perfect. I see the left end coming up, which means as we go out towards the left, we're going down. I see the right edge continuing to go up. As we go off to the right, we keep going up. That matches the end behavior we came up with. And I see some wiggles in the middle. And it looks to me like I've got one local maximum and one local minimum. I just don't know what they are. Crap. All right, that's it. I'm done. Go home. No, I want to be able to figure out what's going on here. Where are these extremes? I could simply start plugging in y values to the left of where I think the minimum or maximum is and work my way to the right. The values will go up and then they'll start to go down, so go backwards a bit and keep zooming in closer and closer, approximating it like I did with Newton's method, right? Above the trace button, it says calculate. Options 3 and 4. My calculator will do exactly that. So if I want to know where the minimum occurs, I give it a left bound. Where do I think is a number that I'm sure is to the left of the minimum? There. That crosshair is now somewhere to the left of the minimum. Hit enter. It asked me for a right bound. See, it put a little flag up there. Hey, you're only allowed to look from here to the right. Now go to the right side of where you think the minimum is and hit enter again. You're making that little strip that we saw in figure 3 on page 276 between those two marks. Those are the only x values you're allowed to look at. Give me a guess. You could start from this right edge, or you could move over a little bit closer. It's your call. You just need to be in that section of the strip to give it a starting point. You hit enter for the third time, and it goes back and forth and back and forth and back and forth until it says, nope, your lowest point is at, I'm going to go ahead and say that's -2. Again, this is a calculator rounding issue. As a matter of fact, if I hit trace and put in -2, 2, I see that that is the minimum value they gave me of -4. So there's my local minimum. I can do the same thing for the local maximum using option number 4. And I will find that the local maximum is at 0, 0. Now, that's all well and good, but it does mean that I do have another option. I'm going to add something to this problem, just one change. What the hell is this? What is that? An interval of x values. I've changed the rules now. And I've said you're only allowed to look between -2 and 4. Because this is a closed interval, I'm including the number -2, I'm including the 4. Change your window on your graph to show only those x values. When I do this, a picture that looks like this. This is the entire picture that I am looking at now. There is nothing else that exists outside this window. Do we have an absolute maximum? Yes. In this window, there is a highest point. Do we have a lowest point? Yes. By including this restriction, a closed interval, I force my function to have an absolute maximum and an absolute minimum because I've cut off the part that would go to infinity or the part that would go to minus infinity. Now, this result actually is true in general. If you have a function that is continuous on the interval from a to b, then it must attain both its maximum and minimum values at some point within that interval. Now, that doesn't mean those are the maximums and minimums. If I change the interval, those could change. What if I changed this picture and said instead of going from -2 to 4, we're only going from 0 to 4? Well, then my minimum value changes substantially, doesn't it? The minimum value is now -4 because we found that point that was the bottom here earlier. So this is actually a really important and very generalizable theorem. We always have an extreme on a closed interval. Now, There is one other thing that's mentioned in this particular theorem. There's a hypothesis here that my function has to be continuous. Why? What the hell does continuity have to do with any of this? Page 278 shows me two pictures. Figures 9 and 10. In figure 9, I don't have a continuous function. I have a jump discontinuity right there at 1. And as we get closer and closer to 1 from the left, there's an open circle there. We don't ever actually hit the y value 3, but we can get as close to it as you want. The limit is 3, but the value isn't. We don't have a maximum. Same thing happens as we get closer and closer to 2. The limit as we approach 2 is 0. Oh, is there a solid dot there? Yeah, there's a solid dot there. We actually do hit 0. We have a minimum, but we don't have a maximum because of the discontinuity. If we had an asymptote, the same thing would happen. So I need continuity in order to enforce this attaining of a maximum or minimum value. So there are now two questions before me. First, if I know we're going to have them, how do I find them? Second, where's the calculus in all this crap? Let me go back to the original picture we were looking at for this. We have a local maximum at 0, 0. We have a local minimum at 2, negative 4. We already worked those out on the calculator. What did we use our derivative to find? In all of the stuff we've been doing, all of the stuff on the review sheet, we're actually asking you to use the derivative. What am I asking you to find? Slopes of tangent lines. At 0, 0, at 2, negative 4, what do our tangent lines look like? Horizontal line. What's the slope of the horizontal line?
0.
Vertical lines don't have a slope. That's got a slope, it just happens to be 0. Horizontal line has a slope of 0. Fermat's theorem. Yes, same Fermat as Fermat's last theorem, but obviously this wasn't the last one. Fermat came up with the following statement. If you have a function and it has an extreme, then at that point, if we have a derivative, value is 0. So with this problem, in order to figure out what those maximums and minimums were and where they were going to happen, I could say, well, let's take a look at this function's derivative. What's the derivative of that function? Leo?
3x. 3x squared minus 6x.
And that exists everywhere because that is a polynomial. So now I can ask, where is my derivative 0? But that's quadratic, that's factorable. I factor out a 3 and an x. And that means either x is 0 or x is 2. And those were the places where we found our extremes, at 0, 0, and at 2, negative 4. X equals 0, and x equals 2. We already know what the vertex of this parabola is. What's the x value for the vertex of this parabola? You did it 15 minutes ago. Turn back in your notes. Negative 4. Let's look at Fermat's theorem. What's the derivative here? And 2x plus 8 is equal to 0, precisely negative 4. Exactly where we saw our minimum. Questions? There is one problem. Right? Where does this graph have a horizontal tangent line? Well, Dom said, I look where the slope of the tangent line means I look at the derivative. If I want 3x squared to be equal to 0, what's my x value? Yes. So I should have a horizontal tangent line when x is 0. Graph this function. We absolutely have a horizontal tangent line at 0. Do we have a local maximum at 0? Do we have a local minimum at 0? So here's my problem with Fermat's theorem. Fermat's theorem tells me where I have a horizontal tangent line. It doesn't tell me where I have an extreme. It tells me where my candidates are. Because remember, that was the if part of the statement. If we have an extreme and my derivative exists, then the derivative has a value of 0. If I know where the derivative is 0, that might not give me an extreme. That's a converse error for those of you that have taken discrete or formal logic, gone the wrong way on your if-thens. But this is a compound if statement. If I have an extreme and my derivative exists. What does the graph of the absolute value of x look like? A V shape. We absolutely have a minimum on this graph at 0. Great, wonderful, fabulous. There's just one problem. You should look at it in the square window so it looks right. What else do you notice about this graph at 0? And that means my derivative doesn't exist at 0. This function has a corner. Where we have corners, we don't have derivatives. As a matter of fact, back in chapter 2, section 7, I believe, where we did the definition of the derivative with the limit, we did this function as an example. And the derivative had a jump in it. There is no value at 0. So here's my twofold problem. I need to know where my derivative is 0, and I need to know where my derivative doesn't exist. And then I need to be able to figure out whether or not those are maximums or minimums or something else altogether, like we saw in x cubed. As a matter of fact, I'm going to give that thing a name. If I go back and I look at the graph of x cubed, let me zoom in here. I can see, I have a very vivid imagination, I can see somebody riding this picture. They're holding on to the neck of an animal and sitting right here at 0, 0, yes? On the little flat spot. We know we have a horizontal tangent line, that's a flat spot. I sit in a saddle on a horse. I'm going to call this a saddle point. It's not a maximum, it's not a minimum, it's just a flat spot. I'm going to call that a saddle point. So up here, I'll make a note that that's a saddle point, not an extreme. But that means I'm going to look for the candidates first. And those are the numbers where either my derivative is 0 or my derivative does not exist. We're going to call those critical numbers. A critical number for my function is an x value where either the derivative is 0 or the derivative doesn't exist. I should be a little more, hang on, there's one other thing. A critical is x equals c. C is in the domain of f of x. So if I'm thinking about like the square root doesn't even exist over here on the left. There are no critical points on the left. All the critical points that would happen have to be on the right. And that means that my local maximums and local minimums and my absolute maximums and absolute minimums potentially show up critical numbers. Finding the points on the graph where we have critical numbers, the critical points of my function, now becomes an exercise in derivatives. One of the examples in the text Chapter 4, Section 1, page 7 has a function x to the 3/5 times 4 minus x. And the reason I want you to write down that you should look at this is because when you take the derivative, you need to do the algebra because you need to know where it's equal to 0 and where it doesn't exist, which means you need to simplify this expression. You have to do the algebra this time because we're doing something with our derivative. I'm setting this thing equal to 0, and I need to figure out where it doesn't exist, which means I need a common denominator. I need to know where the bottom is 0. That's going to give me where it doesn't exist. I need to know where the top is 0. That's going to give me where it's equal to 0. And you'll notice I have a vertical tangent line here in the picture. That's where my derivative doesn't exist. I have a local maximum. That's where my derivative is 0. So I find the options, my critical numbers. I need to do the algebra on my derivative. Questions? If I am looking at absolute extremes, then I have an interval, right? On a closed interval, my extremes can occur at critical numbers. And I guarantee you the local extremes will happen at critical numbers. But the absolute extremes could happen at the edges of my window. So here's an example. Here's the function. f of x is x cubed minus 3x plus 1 on the interval from 0 to 3. I only care about numbers between 0 and 3. Find me the critical points, critical numbers for this function. So I take my derivative, which is a polynomial, so it exists everywhere. I don't have to worry about where f prime does not exist. I don't have to worry about where f prime is equal to 0. I get two critical numbers, plus and minus 1. But I only care about one of them. Well, I'm allowed to throw the negative 1 out. It's not an interval I care about. I only care about numbers between 0 and 3. Now that is an even bigger advantage because it means I can say, oh, I only have one critical number. I need to check the y value at the critical number I care about and at the edges of my interval. So I can make a table to find the absolute maximum and minimum, which I know have to exist. I simply have to plug in these numbers to my equation, which makes my life a lot easier. Into the original function, 1 minus 3 plus 1 is negative 1. 27 minus 9 plus 1 is 19. There's my absolute maximum value occurring at 3. There's my absolute minimum occurring at x equals 1. When I have a closed interval, I can do this with a table. If I don't have a closed interval, this is going to get harder. But I know I'll still be looking for the critical numbers. Ideally, they're actual points on the graph. We'll call them critical points. Example 9 on page 279. There's 79? Come on, turn the right page. No. Example 9 on page 281 does this with trig functions. Big deal. That's why we spent time in trig solving equations of the form trig function equals 0. Because I'm going to use it right here. Tomorrow morning, spread yourselves out. I'll see you then for the exam. If you came in late, please come bring me your homework. I will post all of the keys in the next couple of minutes, and I will see you all tomorrow morning.